going to talk about sample spaces where each event in the simple sample space is equally likely. For example, you roll or die, the chances are equally likely that either a 1 will come up, or a 2 will come up, or a 3, or a 4, or a 5, or a 6. All the outcomes are equally likely. So suppose that the set of events S is one such set. It contains well, let's not say that. It contains 1, 2, 3, all the way up to n. And you might want to think of n as 6. It might be more favorable for you. Again, we're supposing that S is one of these sets where each event in S is equally likely. So it's going to be that S has their property that the probability that I occurs, where I is one of these values in S, I is either 1 or 2, all the way up to n, the probability that I comes up is going to be 1 out of n. If I is 7, the probability that 7 comes up will be 1 out of n. Now, if you think about it, from axiom, let's see what that's going to be. From axiom 3, it follows that the following is true. Let's put it here. For any event E, the probability of E, and this is very key in probability when all outcomes are equally likely. It's the number of elements in E divided by the number of elements in the sample space S. For example, in our above example, if suppose you had an n-sided die. It has n sides. It's very okay for you to hear 6 every time I say n. But please, write n, don't write 6. What's the probability that you get is 3? Well, there's only one element, 3, and it's out of 6, or n. So it's 1 over n. But I don't want to leave this here because this is not always true. Okay, now what do I mean it's not always true? Well, if E1, so now we're talking about a regular die. If E1 is odd and E2 is even, the probability of getting an even, well, there are 3 evens out of 6. I like to call this favorable outcomes. And the bottom is the total number of outcomes. Total number of outcomes. Turns out this is a half. But you know what? The probability of E2, probability of getting evens. If I said evens for this, I meant to say odds. The probability of getting evens, well, there's 3 out of 6. So if S is equal to E1, E2, well, I guess it was. There's 2 events in here, so each one is going to be 1 over 2. Exactly what we're getting. So yeah, it's always going to be that. It didn't, what I was saying is, it's not always going to be 1 over 6. When you talk about a die, the tossing of a die, you can come up with a sample space S where S is not 1, 2, 3, 4, 5, and 6. It turns out that S has 2 elements. 2, 4, 6. That's one event. And the other event is getting a 1, a 3, or a 5. Okay, they're not 1 out of 6. They're actually 1 out of 2. But since they're equally likely, it's 1 over n. There are 2 events, so I got 1 over 2 for each of them. Probability of E1, probability of E2 is 1/2. What about the probability the sum of 2 dice is 8? If you toss 2 dice, what's the probability that their sum will equal 8? The probability that the sum is equal to 8. Well, it's the favorable outcomes divided by the total number of outcomes. Only get an 8, you can get a 1 and a 7. No. I wanted 1 to be first. You can get a 2 and a 6. You can get a 3 and a 5, or a 4 and a 4, a 5 and a 3, a 6 and a 2, and then you say 7 and 1. No. So it is those 5 outcomes that are the favorable ones. It's 5. Now, how many outcomes are there if you toss 2 dice? Well, as you see, each result has 2 entries. The result from the first die, the result from the second die. Well, there's 1 out of 6 outcomes for the first die. It can be a 1 or 2 or 3 or 4 or 5 or 6. And 6 for the second die. When you multiply them, there are 36 different outcomes. Now you can list them 1, 1, 1, 2, all the way up to 1, 6. That's where 1 is first. There are 6 of them. You can have 2 first, and then a 1, 2, and then a 2, all the way up to 2, and then a 6. That's another 6. Of course, you can have 3 first, and then a 1, and 3, and a 2, all the way up to 3, and then a 6. Well, that's 6. But we can do this all the way to 6 being first. 6, and then a 1, 6, and then a 2, all the way up to 6 and a 6. Well, there are 6 6s. 1, 2, 3, the row 4 that I didn't put, row 5 that I didn't put, and row 6 that I did put. There are 36 different outcomes, so it's 5 out of 36. Now, why was I allowed to use this rule? The answer is very simple. The probability of getting a 2 and then a 6 is the same as getting a 3 and a 5. It's just any one random pair. This 36 that I just listed, 1, 1, 1, 2, 1, 6, all the way down to 6, 1, 6, 2, all the way up to 6, 6. There are 36 entries in here. Do you think any one of them is more likely to come up than another? The answer is no. If we're fair die, they're all equally likely. That's why we were able to use that rule. What rule? Probability of the event is the favorable outcomes divided by, let me say it differently or better. It's the number of favorable outcomes divided by the total number of outcomes. Okay, suppose now you have this urn. Probability and urns, they go together. Suppose the urn has 3 white balls and 4 black balls. And you are going to draw 3 balls. You are going to draw 3. And the question is, what is the probability of 1 white and 2 blacks? Well, before you should ever attempt to do a probability problem, you need to understand what the event really is. You're going to draw 3, and you're going to get 1 white and 2 blacks. That is, you can get a white and then 2 blacks. So basically, I'm writing down 2 B's and 1 W. The W can go first. The W can go second. And for the third possible way, the W can go last. These probabilities, that is, the probability of getting a white and then a black and then another black, is the same as the probability of first getting a black and then getting a white and then getting a black. The probability of black, black, and then white is also equal. These 3 are all equal. So why don't we find the probability of getting a white, black, and black, and then tripling that answer? For example, this is not going to be true, but if this is 7 over 11, I don't like that one, 7 over 41, and this is 7 over 41, and this is 7 over 41, well then the probability of getting 1 white and 2 blacks would just be 3 times that common answer. So I'm allowed to just say it's 3 times the probability of getting white, black, black, or it's 3 times the probability of getting black, white, black, or any of these, or the probability, or 3 times the probability of getting black, black, W. Okay, so what is the probability of getting a white, and then a black, and then a black? Okay, I didn't say it, but I should. You know, when it says to just draw 3, it means without replacement. You put your hand in, you take out 3. Now, it's never stated, you know, for completeness it should be stated the balls are the same size. Okay, if the black balls are just huge, the size of a basketball, and the white balls are the size of a ball bearing and a roller skate, well, when you put your hand in, you'll probably come out with a black ball. Probability of getting 1 white out of 3 picks is going to be very small. But they're all equally likely. Alright, so it's 3 times something. It's 3 times this. The probability that you pick a white first, well, in all, there are 7 balls. 3 of them are favorable. says 3 out of 7 chance that you get a white. And you did. There are now 2 whites. So when you go to pick the second time, there's only 6 balls remaining, 4 of which are black. But you picked it, so now there's only 3 blacks. When you go to pick the third ball, there's only 6 left. Well, that can't be. There's only 5 left. I can even tell you which 5. The 2 whites and the 3 blacks. There are 5 balls remaining, and 3 of them are black. And there's your answer. You can say this 3 or any of the other 3s in the numerator goes into the 6 2 times. And then you can say 4 over 2 is 2. So how I see it, it's 3 times 2 is 6, times 3 is 18, divided by 7 times 5, or 35. Now, if you don't believe that the probability of all these 3 were the same, well, let's look at another one. Black, white, white. Sorry, that's not 2 blacks and a white. Let the third one be black as well. Black, white, black. So we want to get the same answer that's in between these big brackets. Well, the first ball, you're picking from 7. Remember, there are 3 whites and 4 blacks. You're picking from 7, and there are 4 blacks. Okay, you picked one of the blacks, so now there's 3 left. In all, there are 6 balls remaining. You got a black, now you want to get a white. Well, there's 3 whites. Okay, now there's 2 whites after you pick that second ball, which was white. Now there are 5 balls remaining. 2 whites, 3 blacks. And you want to get a black. Well, there's 3 of them. Well, maybe the numerators and the denominators are in different orders, but it's the same as what we got on the bottom. Just going to rewrite it again in the same order we got. The numerator has this 3, a 4, and this 3, so it is our numerator. It has a 3, a 4, and it's 3. The order doesn't matter. In the bottom, 7, or 6, and a 5. 7, 6, and 5. It's the same answer. If you computed the probability of black, black, white, you'll get the same answer. 6 over 35. And why do I have 18 over 35? Because this probability is 6 over 35. When I multiply it by 3, I get 18 over 35. Suppose you want to form a committee. Now, the committee should have 5 people, and you're choosing them from 6 men and 9 women. You want to make. You want to make up a 5-person committee. From nine women and 6 men. What is the probability that he picks 3 men and 2 women? Now here the order doesn't matter. It isn't like first, second. The probability of getting a black marble and then a white marble and a black marble, that event, the event is not the same event as getting a white, a black, and then a black. The probabilities might be equal, but they're not the same event. Turns out that probabilities were equal. All right, so now in the bottom we have 15 people. From 15 people, we want to choose 5. That's the total size of the sample space. How many different 5 people committees can you pick or make from 15 people? Okay. Now we want a favorable. Well, you need to do 2 things. From the 9 women, you want to pick 2. And then, from the 6 men, you want to choose 3 men. There's your answer. If I'm not mistaken, it's just a name, so it really doesn't matter. But this form that I wrote it in is called Hypergeometric. From the 9 women, we chose 2 of them. And then from the 6 men, we chose 2. And this is the number of favorable outcomes. What's in the numerator, and you multiply those 2 numbers, that result will be the total number of 5 people committees you can pick from 9 women and 6 men that have 3 men and 2 women. And when you divide it by 15, choose 5, you then have the probability of getting 3 men and 2 women. Okay, let's try another one. It's the probability. What is the probability of getting a 5-card, let me say it differently, getting a straight in a 5-card poker hand? Okay. I've seen a lot of students who could, in theory, do these type of problems. But they couldn't do them because they didn't know the makeup of a deck of cards. It's really important that you know the makeup of a deck of cards. There are aces. Aces for right now we think of as ones. You have aces, 1s, and 2s, and 3s, and 4s, and 5s, all the way up to 10. Jack is like the 11th denomination. Queen is the 12th. King is 13. There are 13 different denominations. Ace, king, ace, 2, 3, 4, all the way to king. Now, ace is also the highest card as well. Now, when it comes to each of these denominations, there's 4 cards of each one in the deck. There is the ace of spades, the ace of clubs, the ace of diamonds, the ace of hearts. There is the 2 of spades, the 2 of clubs, the 2 of diamonds, the 2 of hearts. All the way down to the king of spades, the king of clubs, the king of diamonds, the king of hearts. 13 times 4 is 52 cards. There are 52 cards. So in the bottom, I'm going to put the total number of possible outcomes. What's an outcome? A 5-card poker hand. From 52 cards, you want to choose 5. Now, what is a straight in a 5-card poker hand? Well, That's when the cards go in order. Ace, 2, 3, 4, 5. Or 2, 3, 4, 5, 6. Or 3, 4, 5, 6, 7. All the way down to 9, 10, Jack, Queen, King. And as I said, an ace is also the highest card as well. 10, Jack, Queen, King, Ace. Now, if your teacher gave this problem on an exam and you didn't know that ace can also be after the king, your teacher really should mark that right. Well, this is the first straight you can get. Oh, look, there's an ace there. That's the second straight you can get. Oh, look, there's a 2 there. That's the third straight. Look, the first or smallest values is 3. And so on. And so on. This is a straight. It's the 9th straight. You can get 10 different straights. Okay? So, and they all have the same chances. The chances of getting this straight is the same as getting this straight. It's the same as getting that straight. They're equally likely. So in here, I'm going to put the probability, say, of getting that straight. You don't like that one? Wonderful. Find the probability of getting that straight. But you need to multiply it by 10. Or if you didn't realize the last one, you multiply by 9. Your teacher really shouldn't mark you wrong just because you don't know how to play poker. Unfortunately, some teachers do, and it's completely unfair. So depending upon how you think of it, that 10 can be a 9. Now, what is the probability that you get an ace and a 2 and a 3 and a 4 and a 5? What is the probability that you get that? So you want to get 5 cards. The first card, you want to be an ace, or any one of these 5. The order doesn't matter. Well, that can happen in 1 of 4 ways. And the next card can happen in 1 of 4 ways. Okay, it's just 4 to the 5th. There's 4 to the 5th different ways of getting that poker hand. Ace, 2, 3, 4, 5. There's 4 to the 5th different ways. You can get the ace of spades with the 2 of spades, or the ace of spades with the 2 of clubs, or the ace of spades with the 2 of diamonds and the 2 of, or the ace of spades and the 2 of hearts, or you can get the ace of clubs. You can get the ace of clubs with the 2 of hearts, or the 2 of clubs, or the 2 of diamonds, or the 2 of hearts. And then you can do the same thing with the 3s and the 4 and the 5. There's 4 to the 5th different ways of doing that. And that's your answer. This here is the probability of getting a straight in a 5-card poker hand. Now, some poker players may say, well, you included straight flushes. Well, that's also a straight. That's also a straight. Okay. What about now the probability of getting a full house? What is the probability of getting a full house? What's the probability of getting a full house in a 5-card poker hand? Well, Again, there are 50 to choose 5 different 5-card poker hands. Now, what on earth is a full house? Well, it's 3 of a kind along with 2 of a kind. Could have put, I could have put the Q's first. I can put a 2, a Q, a 2, a Q, and a 2. As long as there are 3 of one kind and 2 of another kind, it's a full house. Now, if you were going, I gave you a deck of cards, shuffled, and I said, pull out, you can look at the cards, pull out 5 cards that make up a full house. What are the things that you would have to think about and do? The first thing is you need to pick the 2 denominations. The second thing is you need to pick 3 of one denomination. And the third thing you need to do is you need to pick 2 of the other. Pick 2 from other denomination. Pick 2 from the other denominations. And I guess what you need to do, maybe I'll call this steps 3 and this the 4th step. So from the second step is decide which is 2 of a kind and 3 of a kind from the 2 that you pick. Okay. So now there are 13 denominations. You need to pick 2 of them. Now you need to order the 2. This one's going to be the 3 of the kind. That one's going to be the 2 of the kind. Or that one's going to be the 3 of the kind, and this is going to be the 2 of the kind. How many ways can you arrange 2 numbers? 2 factorial. So if you picked 2 and Q, you have to decide which is going to be the 3 of the kind, which is going to be the 2 of the kind. That can be done in 2 ways. Now, from the 2's, from the 4 2's, you want to pick 3 of them for the 3 of the kind. From the 4 Q's, you want to pick 2 of them for the 2 of a kind. There it is. There it is. Try this other problem. It's a very interesting problem. Suppose you go to a party and you want to know what's the probability that two people at this party have the same birthday. So let's formally state it. N people are in a room. What is the probability? Now, we'll do the complement, that no 2 people share their same birthday? What is the probability that no two people share the same birthday? Well, the first person, they can have 1 out of 365 birthdays. The second person can have 364 birthdays. Their birthday can be on one of the remaining 64 days. Now, two people are in there with different birthdays. The next person can have this person's birthday or that person's birthday. That person, the third person, can have their birthday in any one of 363 days. Now, the question is, remember there are n people. How many different birthdays can this last person have? You need to be clever. You need to look and see. This was the first person. This was the second person. This was the third person. And you say, oh, look at this. Look at this. When I add up those numbers, I get 366. When I add up those numbers, I get 366. When I add up these numbers, I get 366. Over here is going to be an n. Well, what should go in these brackets so they add up to 366? Well, you want 366, but you don't want to add the n. Take it away. 366 minus n plus n, that's 366. Okay. This is the number, that's the favorable number of outcomes for two people in a party of n people to have different birthdays. Now I need to divide this by the total number of outcomes. You have 365 people in a party. The first person can have their birthday in any one of the 365 days, no leap year. The second person can have their birthday in any one of the 365 days. It's basically 365 to the n. Now, one would ask, so this is a probability that in a party of n people, that no two people have the same birthday. Now, either two or more people have the same birthday, or no two people have the same birthday. So two or more have the same birthday. Well, this probability and this one that I just wrote down on the bottom, they're complements. That is, they add up to 1. This is 1 minus the probability that no two people have the same birthdays. All right. Now, it turns out that this answer is less than a half whenever n is, you need to think if it's just bigger than or equal to. It must be equal to. Bigger than or equal to 23. If you have 23 or more people, then be less than or half, then no two people have the same birthdays. Well, if this number is less than a half, 1 minus, if you have $1 and you take away, you spend less than half $1, you'll have more than half left. This is greater than a half if n is bigger than 23. That is, the probability that two or more people have the same birthday is bigger than a half if the number of people in the room at the party, wherever, is 23 or more. And this is a surprising result. This is a very surprising result because 23 is nowhere near 365. People, including myself, were kind of surprised that that was the case. It just doesn't seem like it should be the right answer. Okay, the next problem is rather interesting. Suppose you have a deck of cards and you turn over one card at a time. And then eventually the first king comes up. We want to know what's the probability that the next card is another king, say the king of spades. The probability that you get the king of clubs or the two of hearts. So again, you turn over one card at a time, and then when the first king is turned over, we're concerned about the very next card. What's the probability that the very next card is the king of clubs or the two of hearts? A king, a non-king. And so now, when you do probability, the key thing with probability is to understand or to come up with a clever way of thinking about this. These are 51 cards. Let me put this down more neatly. These are 51 cards, and here is the first king. Okay. Now, I want to know the probability that the next card is the two of hearts or the king of clubs. Okay. Now, imagine we didn't include the two of hearts. Let us work on this probability first. Suppose we did not include the two of hearts. There are 52 cards. You remove the two of hearts. In front of us are the 51 cards. Now, this is the first card, this the second card, the third card, the 50th card, and then the 51st card. Now, we are going to put the two of hearts somewhere in this deck. We could put it after the first card, or after the second card, or after the third card, or after the fourth card, or after the fifth card, all the way up to after the 50th card, or after the 51st card. That's 51 positions we could have put the cards. We could have put the two of hearts in at the very bottom of the pile, the last card. But you know what? We could have also put it in the first position. There are 52 different positions that we can put the two of hearts in. Only one of those 52 comes right after the first king. Now, if you play the game with the king of clubs, you can give the same argument. There are 52 positions that we can put the king of clubs. And only one of those positions is after the first king. they both have the same probability. They're both equally likely. The card that comes after the first king can be any of the remaining 51 cards. Of course, if this is the king of spades, the very next card can also be the king of spades. One deck, one king of spades. Okay, the next problem I like. Suppose there are 40 students in a class, 20 boys, 20 girls. You're going to go on a bus ride, and you want to, the young kids don't like the opposite sex too much. If you put boys next to one another, they'll talk. You put girls next to one another on the bus, they'll talk. You put a boy and a girl on the bus, we're assuming they won't talk. In fact, let's assume they won't talk. So you have a class that has 20 boys and 20 girls. And you want to seat them on the bus. So, you know, our bus, it has a row of seats here. It has the aisle that you walk down, and then it has another row of seats. And we're going to assume that each bench seat can hold exactly 2 people. Or that we're just going to put 2 people, a boy and a girl. And the question is, how many different ways can you do this? How many different ways can you seat the 40 students where a boy and a girl are always sitting next to one another? So one way of doing this, again, like I said earlier, the key thing about probability is to think of clever ways of how to arrange this. Suppose those are the 20 boys and those are the 20 girls. Well, there's 20 factorial ways of arranging the boys, and there are 20 factorial ways of arranging the girls. And the first 2 will sit here, and the second pair will sit here, and the third pair will sit here. The 10th pair will sit there. The 19th pair will sit here, and the 20th pair will sit there. Okay. So that's the number of ways of grouping the boys and girls into 20 pairs. But now, you know, you have boy 1 and girl 1, and you want them to sit here. Well, you know, there's a window here, and a window here, and a window here. You know, there's windows. And there's the aisle. You know, some people like the aisle, some people like the windows. In other words, once you have the 2, the way you seat them matters. You can have boy 1 by the window and girl 1 by the window. Or girl 1, boy 1. The same for this, the same for this. There are 20 benches, 20 pairs of kids. There's 2 to the 20 ways of arranging them once you decide what seat number they go in. Like, this is seat number 1, seat number 2, 3, bench 4, maybe I should say, bench 5 and 6 and 7 and 10, and bench 11 and 12 and 13, eventually 19 and 20. In each case, you could order or seat the 2 children 2 factorial ways. And 2 factorial is just simply 2. Okay. So now, the probability that you get a boy, girl, well, this is the number of ways of arranging them. 20 factorial times 20 factorial is 20 factorial squared. Now, in the bottom, we have to put the total number of ways of arranging the 40 children. How many different ways can you arrange them? Well, if you just put them in random order, 1, 2, 3, 4, 5, 6, 38, 39, 40, you say, so now, wish I didn't erase the bus. Let's put the little bus back. These are the windows. Bench seat. You can say 1 is the aisle. Well, okay, 1's the window, 2's the aisle. Here's the aisle. And then 3 and then 4 in this bench. And in this bench, you get 5 and 6, and then 7 and 8. I mean, if you think about it, if you've been on charter buses, if you think of airplanes, the seats are numbered. The seats are literally numbered. So there are 40 factorial ways of arranging the 40 students. This is the first student, the second student, the third student, the fourth student, eventually the 39th, and the 40th student. Well, what better method than to say student 1 goes to seat number 1. Student 2 goes to seat number 2. Student 3 goes to seat number 3, etc. So you have to divide by 40 factorial. And there's the answer. And this completes the section on sample spaces where all outcomes are equally likely. Now, I haven't talked about it in a little while, but the chances that you sit here or there is the same chance that you sit here or there. They're equally likely. Okay, you're equally likely to get a window seat as an aisle seat, to sit in the front of the bus as opposed to sit in the back of the bus or the middle of the bus. They're all equally likely. Okay, I hope you're having fun with this stuff.